Welcome to Lecture 3 on acid deposition and thermal pollution. I miss everyone and hope you're doing well. It's Friday and it's a new note day. Um, so to begin with, before we start this lecture, I want to make sure that everybody has seen the two questions that are going to be on your FRQ on May 18th. Design an investigation and propose a solution. And we're going to kind of look at both of those today. Make sure that from here on out, we really focus on those topics. So let's start with acid deposition. You guys remember a little bit about pH. We looked at pH in a couple of different units so far. Remember, we talked about acid mine drainage. We talked about how acidic solutions can make metal ions more soluble in soil. And if I have water that's acidic, it might be outside the range of tolerance for aquatic organisms. So the first thing we want to realize is that pH normally is a little bit acidic. It's not neutral, or excuse me, rainwater is normally a little bit of acidic. It's not neutral or 7, and that's because of natural carbon dioxide in the atmosphere. However, from burning coal, we create SOx, that primary pollutant, and from burning mostly gasoline, we create this NOx, a primary pollutant. All acids are therefore secondary pollutants. So technically, I could be making this natural carbonic acid, but then I make sulfuric acid and nitric acid as well. So if I take a look at where in the United States acid deposition is a problem, look at some of the low pHs I have here. I have in the kind of the industrial steel belt in the Midwest. I have pHs down in the low to mid 4 range. That's obviously quite acidic. And then in areas of the country where I have very little industrialization, I tend to have more of those again, even though this might look pretty acidic. That's just what the pH of natural rainwater is. Remember then, that's one of the reasons that we can chemically weather rock and have that rock break down to form soil. So the big idea that we want to talk about in terms of pH is that idea of range of tolerance. So if I have to describe an environmental problem or explain how something happens and the impact of that, remember how valuable that term is on an FRQ. So different animals, in this case aquatic animals, have a different range of tolerance for pH. So clams have a very narrow range of tolerance. The minute I get a pH below 6 or more and more acidic, they simply won't survive there. Mayflies have a pretty narrow range of tolerance. If you were out on the Yellow River water testing field trip, we saw that mayflies, if we found those were indicators of pretty good water quality. Acid rain forms then as this secondary pollutant when it's literally what we call an acid gas, when that acid gas combines with water vapor in the environment and the resulting precipitation is acidic. Had you been in class, I would have done this super cool demonstration for you. And if you need a little geeky chemistry woman fix, you can click on the link and watch it. But basically what this is calcium carbonate. This is limestone. And on the exam, I can say calcium carbonate, limestone, I could even say lime, and they would understand what I was looking at. So she put in some simulated acid rain with a universal indicator in it, and she poured that through all of these marble chips, and they really neutralized the resulting lake water. So the idea is that if I have areas where the underlying soil is made from limestone, then that limestone or calcium carbonate somewhat neutralizes the impact of that acid rain. And again, I kind of made that point already, but this is a connection that we want to make in terms of acidity in soils. So just a couple of the impacts. It can damage aquatic ecosystems, which we saw, that idea of range of tolerance. In terms of a terrestrial ecosystem, it can damage the leaf tissue. That's just a simple way of expressing that you get that there's something besides that pollution is really, really bad. It damages the plant tissue of leaves, and therefore they are not as able to do photosynthesis and turn carbon dioxide into sugars. It wears away marble statues. That's one of our other little essential knowledge statements here about the impacts of acidification. It can cause corrosion to man-made structures. And we actually see that happening in a lot of European cities, very ancient carvings and sculptures that are being deteriorated through acid rain. There's been a lot of renovation of them, but still a problem. So remember that when we started, we said that one of the big FRQ prompts is going to be about solutions. One of your whole FRQs is going to have a number of points on solutions. So to be honest, one of the simplest things is to not burn coal, because one of the major sources of acid rain is SOx, and that comes from burning coal. But remember, as a solution, I can never simply say, well, don't do something. Instead, I can say switch from using coal and use a renewable source of energy like solar or wind that does not have SOx emissions. Make sure you explain why switching to that renewable. I'm not burning anything and emitting SOx. I could even, as a solution, say conserve electricity. I could buy an Energy Star appliance and have to burn less coal to generate less electricity and have less SOx emissions. I can restore a damaged ecosystem by adding lime. There are some countries that have tried to do this, or some regions that have tried to do that. It's really expensive, and it's often only a short-term fix. Like it'll have a quick, immediate remediation of that acidic area, but it's not typically a long-term fix. Obviously, the advantages are that it is going to neutralize the acidic impact of that acid rain. I can pass legislation, or in this case, for a solution, I would say enforce the Clean Air Act. There's already legislation that exists, so I could say, oh, SOx, that is the S in nose clamp. So if I enforce the Clean Air Act and reduce SOx emissions, the primary pollutant, I will naturally reduce the formation of the secondary pollutant. Fines for polluters, and even an air pollution control device, a wet scrubber. It kind of may sound familiar from when we did incineration of waste, but we're going to talk about that in our last lecture. And then the next topic that we're going to cover today is a temperature or a thermal inversion. So let me kind of explain to you what happens normally. And the key thing here is that this is a big city with a lot of really tall buildings that sort of block airflow, and mountains can do the same thing. So normally when I don't have this thermal inversion, and by the way, this is a natural phenomenon, it is exacerbated by the pollution that we made, which you'll see in a minute, because it traps the smog and particulates down where we're breathing the air. But the actual inversion itself is just a natural climate phenomenon that happens in certain areas. So normally sunlight strikes the surface of the earth and it warms the surface of the earth. And so I have warm air down near the ground. That warm air is low density. Remember, those particles are far apart. That less dense warm air rises. So if there's a lot of that ozone and photochemical smog and a lot of particulates down here at ground level, normally the pollutants are still there, but it's all about concentration in terms of us breathing them in. That warm air mass lifts and it takes and disperses those pollutants. When I have a thermal inversion, I might have, like, let's say this is Los Angeles. They're kind of known for their thermal inversions and these really drastic air pollution days where people are told don't even go outside, or where, now that we all understand what they mean by an N95 mask, wear a mask, a respirating mask when you go outside and breathe the air. So in Los Angeles, I might have a cold, dense air mass come in from the Pacific Ocean, and I might be under a high pressure climate system. The main thing is that this cold air mass comes in from the Pacific. That's dense air that's just hanging down there. So I've inverted my layers. I've flipped them. Normally I have warm air down at the ground and cold air up higher. In a thermal inversion, just this cold air mass that comes in traps that air. the warm air layer ends up being above it because there's under high pressure that's pushing down. So all of these pollutants get trapped down here. And it's a big human health concern in areas, large urban areas that have a lot of traffic, because that's where they get a lot of smog, and where I have really tall buildings that are going to block that wind flow, or mountains that block that wind flow. So let's try a couple of practice questions. I'm not going to put up any formative quizzes since we don't have multiple choice questions on our national exam. Instead, I'm going to have you do an extra practice FRQ. So I'll just give you a couple of quick content checks right here. Which of the following best describes the process shown in the diagram? And we just went over that. So less dense warm air creates a temperature inversion between more dense layers, trapping pollutants near the ground. Air pollution experts set up a monitoring program to determine the amount of particulate matter leaving a farmer's field after crops were harvested and the soil was bare. She set up high volume air samplers 10 meters from each edge of a square field and collected samples weekly for 2 months. When she looked at the data, she was surprised by how much particulate levels varied, both from the bare field to the other field that hadn't been harvested. She was surprised by variation from site to site as well as over a period of time. Which of the following parameters would have been best to measure to help her explain the variation in her data? This is kind of an experimental design question. And the wind speed and wind direction, because remember those particulates are going to be carried quite a great distance from the area where they were generated. I think we have one or two more. Which of the following would most likely neutralize the effect of acid rain on bodies of water? Again, even though you're not going to have multiple choice on the exam, they could present a scenario to you about acid rain and ask you to present and justify a solution. And we have that forest underlaid by limestone. Oh, one more. In 1950, the pH of a pond was 8.2. By 2000, it had decreased to 5.2. So right away, you're thinking lower pH, more acidic. The effective short-term remediation strategy for the pond would be short-term, something really quick. And we talked about this as well. Add calcium carbonate to the pond. All right. Good luck on that section of the lecture. I will be posting another lecture on solutions and indoor air pollution. See you next time, guys.